we're going to talk about growth rates. Because much of what Wall Street does is swap between a certain amount of money right now or a flow of money at future dates. How exactly? There are a lot of details, but at base it's really simple and it depends on interest rates. Interest rates are the price of the future. Literally. How expensive is tomorrow? The interest rate is going to tell you. Farmers always have to borrow money because their costs come early in the growing season, while their revenues only come when the crop is sold. But we start with growth rates. That's one of the biggest and most important concepts. It's one where we have to do some calculations since our intuitions completely fail. A growth rate of 5 or 10% per year doesn't seem like a big deal, except over a longer time span. I mean, if you grow your skills by 5 to 10% per year, that doesn't seem transformative, but it means that after about 10 years, you've doubled or more than doubled your skill levels. That is a huge difference. In so many things, slow, steady growth is a great long-term strategy. Patience and discipline are superpowers. Because it's slow but very powerful, most people don't appreciate the force of steady growth year after year. We need to use some math to really appreciate it. If you save $500 and that's invested and grows by 5% each and every year thereafter for 15 years, how much is that going to be worth? How do you solve that question? Often the case, we just break it down into little parts. Each little part we can manage. I'm not smart enough to do it all at once, but I can do it bit by bit. Calculate growth after 15 years, I start by calculating growth after 1 year. If I have $500 and that grows at 5%, then after 1 year, how much do I have? Well, 5% of 500, add that to the original 500. So 1 plus 5% times what I started with, 500. Calculate what happens after 15 years. I'm just going to do that again and again. After 1 year, I have an answer. Then how much is that going to be after 2 years? It will be 1 plus 5% multiplied by 1 plus 5% again. I can have the same problem. I'm going to start with this number, add 5%, get another number. Do that 15 times. Now that's a lot of button pushing on my calculator. Maybe you don't want to do it. You might want to say, hey, is there an easier way? Yes, there is. I'll talk you through it because compounding, just doing the same thing over and over again, is the only fact we need to figure out a whole bunch of different formulas. They may look a little ugly. Okay, a lot ugly. But they're actually perfectly straightforward. Start with Z dollars, and that's going to grow at a rate R, where the problem has maybe Z is 10 million or Z is 500, R is 5%, something else. Z dollars growing at a rate R. What is that going to be after 1 year? That will increase by that percent. So in our formula, that's R times Z. And I'll have the original value Z, so after 1 year of growth, I have Z times 1 plus R. After 2 years, I don't do anything new, I just solve recursively. Start with an amount Z, at N, Z times 1 plus R, but this time the new Z was the original Z times 1 plus R, so after 2 years, I have Z times 1 plus R times 1 plus R. Simplify that formula to write Z times 1 plus R squared after 2 years. Do that a few more times, start to figure out, hey, it looks like there's a pattern. Yeah, there's a pattern. After T years, I would have Z times 1 plus R to the T power. So after 10 years, put in T equals 10. After 15 years, set T equals 15. Now, one of the things to notice here is the answer depends on Z in a simple multiplicative way. If you know how $1 grows after 2 years, then you know how any other amount would grow, 100 or 10,000 or whatever. In the math notation, I can X Z outside the parenthesis. Just remember the math rules about percentages. 5% is 0.05 as a decimal, 10% is 0.10, 2% is 0.02, etc. If that's too much calculation, and I know honestly I can't do powers in my head, most people want a simple approximation that you can do in your head just to be able to think the problem through in a very approximate way. That's the rule of 70. I cannot solve these sort of polynomials in my head. If I want to do that in a calculator, I turn my phone to landscape mode or do it on a spreadsheet. There are options, but you might want a simpler way. That's the rule of 70. That rule says the initial amount will double after about 70 divided by r years. Really, the only complication here is we're keeping the percent as a regular number. Do not convert 5% to 0.05, just use the number 5. How long would it take to double an investment to create a 100% return at a rate of 5%? I don't know, maybe you guessed 20 years. That would be if there's no compounding. But with compounding, it's about, 70 divided by 5 is 14, so about 14 years. Take about 14 years to double an initial investment. If the interest rate were 10, then the investment would double in 70 divided by 10, 7 years. 3.5%, the initial investment will double in, what's 70 divided by 3.5? Well, that's 20. These are all approximations, but they're useful for doing estimation kind of in your head. Now, note some complications. Start with a little terminology that you often hear if you listen to the news or people in the finance industry. Talk about basis point. A basis point is 1/100th of a percentage point. So 25 basis points is 1/4 of 1 percentage point. And if the interest rate changes from 3% to 3.25%, that's a 25 basis point increase in the percentage. Sometimes people just say bips. Talk about 50 bips, 25 bips, or 1 bip. Now, the reason you and I don't ordinarily work with basis points is because you and I ordinarily are dealing with amounts of money where 1 basis point just don't matter. I got $100 in my bank account, then a basis point is 1 penny. So yeah, a penny more or less ain't going to change nothing in my life. On the other hand, if you work for a major financial institution, then a $100 million transaction, a basis points or 2 starts to add up. Fancy people tend to worry about things like that. Now, if you've ever read the fine print of a financial contract, such as a credit card agreement, you might see something about rate of compounding. Annual compounding is where an amount of money grows to 1 plus r after 1 year. But there could be semi-annual compounding, where after 6 months you get half the interest, and after another 6 months they compound it again. Or you do that every quarter, so after 3 months you get 1/4 of r, then another quarter after 3 months, and etc. After a year, the initial investment would grow to 1 plus r divided by 4 to the 4th power. You could do it every month, in which case it's 1 plus r over 12 to the 12th power. You could do that 360 times, so it would be 1 plus r over 360 to the 360th power. You could even, and here's some math wizardry, compound an infinite number of times. Mathematicians figured out, in the limit, the calculation does converge to some answer. It converges to something involving the number e. I hope you remember this crazy e demon. E is this odd irrational number, transcendental, first used by mathematicians John Napier and William Oughtred in the early 1600s. Jacob Bernoulli derived it. Euler popularized it. E is the limit of 1 plus 1 over x to the x power as x goes to infinity. Now, E, it turns out, pops up in any number of completely different places. It's kind of wackadoodle. It's also the infinite sum of 1 over x factorial. Other places, it's the expected minimum number of uniform 0-1 draws needed to sum to more than 1 in expectation. The area under the curve, 1 over x, from 1 to e is exactly equal to 1. Sometimes we write e to the r power, sometimes e x p bracket r if the stuff in the superscript is important enough to get the full font size. The opposite of e is a natural log, so if I take the natural log of e to some number x, the result is x. Natural log is the inverse, which is why we often take logs when showing the graph of a number that grows exponentially. Well, let's get down to the details. How does compounding actually change the outcome? What's the difference after a year, whether money grows by annual compounding or semi-annual or whatever rate, even infinitely? You just do the math. If I compound once every once per year at a 5% rate, then I get 1.05 at the end of the year. If I compound twice, then after 6 months, I get 2.5%, and after the next 6 months, I get 2.5% of the original 2.5% as well, so I'm left with 1.050625, a little bit more. If I compound 4 times, I get 1.05094. 12 times, or 250 times, or 360 times, I get a bit more. Sidebar, why 360, not 365? Isn't that how many days are in a typical year? Well, going back to the ancient Babylonians, they figured out there were about 360 days in the year and then a bit more, which is why we use 360 degrees in a circle. Thank you, Babylonians. But anyway, sorry, little diversion. You compound at a higher frequency, you get an increasing amount, but it does converge. Look at 1.05, 1.0506, 1.0509, 1.0511, 1.0512. Those increments are getting smaller and smaller. So as if I compound an infinite number of times, at the end of the year, I'd be left with 1.0512711. Well, the decimal goes on and on and on and on forever because E is a transcendental number. But back to the question, do ordinary people care? Again, no, not really. If you put $100 in the bank, you'd have $105 at the end of the year if it's compounded once. Or you have $105.12, almost 13, if it were compounded an infinite number of times. 12 cents ain't going to change my life. For ordinary people like you and me, it just don't matter. Fancy people who have a lot of money are going to watch every little bit because those numbers do add up. If you work at a bank, you will pay attention to compounding.